In this question, we're given that there is a polynomial pz. It's a polynomial pz, and all the coefficients are real. It says real coefficients. And we're given that the equation pz is equal to 0, that this has a root, right? This has a root given by r e to the I theta. And where the r here is a positive number, and theta is an angle between 0 and pi. So we are given that it has a root like that with this description. Okay, and question is to write down another root. Write down another root in terms of this. Write down another root, and also to show that this expression z squared minus 2rz cosine theta plus r squared, to show that this is a factor. It's a factor to this polynomial. So that's the first part. And then there are two other parts. Now in the part 2, we have to solve this equation. Z to the power of 6 equals to minus 64. Okay, and we must give the solutions in the form r e to the I theta, and where r is positive and theta must be between, let's see, must be more than minus pi, less than or equal to pi. So I have to put the equation, the solutions in this form. And last part of this, we want to write this expression x z to the power of 6 plus 64. Write this as 3 quadratic factors. Okay, 3 quadratic factors, and coefficients must be real coefficients, and we mustn't use sines or cosines for this, just numbers. Write down the real coefficients and use just numbers for the coefficients. Okay, so don't put it in terms of sine or cosine. Real coefficients. Just use numbers for those. Okay. So let me start with the first part. So if you're given that pz has real coefficients, now if pz has real coefficients, then and r is r e to the power of I theta, right? If z equals to this number is a root, right? Then the complex conjugate z, there are different ways to write this. I'm going to use z, let's see, maybe z with a line on top. Okay, so z with a line on top is the complex conjugate. Or I could also use z star. Okay, I'm just going to use this line and so if z equals to this is a root, then the complex conjugate is also a root, and the complex conjugate is given by this. I change the angle to negative. So now I'll after going through the solutions, I'll briefly explain why this is the case. Okay. For this question, we don't actually need to know why. We just have to, or we don't actually have to say why. We just have to state, just have to write down another root. So this is the other root. Okay, this is our roots. So that's part of the answer. And then we want to show that that the given that quadratic expression is also a root. So what we do next, okay, we want to show, so this is one part is answered. Then we want to show that z squared minus 2rz cosine theta plus r squared. We want to show that this is a factor. So to show that this is a factor, since this and this are roots, it means that if this is a root, then z minus the roots must be a factor. So that's from the factor theorem. Okay, and z minus that must also be a root. So z minus r e to the minus I theta, that must also be a root. Now if you have done some exercises on expanding such expressions, you might be able to see that when you expand this and simplify, you would actually get exactly this. So let me just run through this. If I expand this, I'll get z squared. Okay, I'll get minus okay, let's see, z times z is z squared. This times this is minus zr e to the I theta times that, and that times that is minus zr e to the minus I theta, and that times that would be plus r squared, and ei theta times e minus I theta would be 1. Okay. So this would be z squared minus factor out the z r gives e to the I theta plus e to the minus I theta plus r squared. Okay, and finally z squared minus that plus that would be 2 cosine theta, so 2zr cosine theta plus r squared, which is the same as this. So that's the answer, next part to the answer. Okay, so the first part is done, part 1 is done. Now let's go to the part 2. In part 2, let's see what we need to do. Okay, we need to solve z power 6 equals minus 64. Now in order to do this, we need to give the solution in the exponential form. So to do this, we could start by putting this into exponential form. 64. So the minus here, let's make use of e to the pi, e to the I pi equals to minus 1. Okay, so the minus sign here mean that, let's say if we think of the complex plane, x here and I by here, or the Argand diagram, then the minus 1 would be here, minus 1. So it's like an arrow like that, and the angle theta would be pi radians. So this minus sign here, therefore, is the same as e to the I pi. Okay. Now to find z, we need to root this. We need to take the 6th root of this of the two sides of this equation. Now, if it's z to the power of 6, we would expect that there are actually 6 answers, 6 different answers, or up to 6 different answers. But if I just take the roots of this directly, or the 6th root of this directly, I'll just get one answer. So what I need to do is to put this in another form, to write this as e to the power of I pi plus 2n pi. Now 2n pi just means the whole number n times 2 pi, which is times 360 degrees. So on the Argand diagram, it just means that if I add 360 degrees to this, I come back to the same angle. So if I add any number of 360 degrees, it's still the same angle actually. So by adding 2n pi to this angle, I've not changed anything here. This is still minus 1. Okay, but the purpose of adding the 2n pi is that if I now take the 6th root, that means put this to the power of 1/6 here and here, then I can actually get out all the possible answers. So let me write this out. So if I raise this to the power of 1/6, I'll get this one, 64 to the power of 1/6, and then e to the I, this divided by 6. So I get pi over 6 plus 2n pi over 6. Now if I do this, then for different n's, I can actually get different answers for this. But they're not all different. They're only different for maybe for 6 possible values of n. Okay. So for example, if I take n equals to 0, 1, up to 5, then each of these will give a different answer for this. But if I take n equal to 6, then the answer for this would be the same as when n is equal to 0. Because when n is equal to 6, 6 over 6 is 1 and I get 2 pi. Then it will be again like going one whole round back to the same angle. So this is one possible set of values of n that will give all different answers for that. Okay. Now, let me simplify that part. So 64 to the power of 1/6 is actually 2. So 2 e I pi over 6 plus that would be n pi over 3. But there is a condition in this question. The condition is that if we call that r and call that theta, the condition for the answer is that the question wants theta to be more than minus pi, but less than or equal to pi. So let's check whether these values of n would give theta in the right range. So what would be an easier way to sketch this? Let me clear this. Okay, that's the complex plane again. That's x, that's iy, the imaginary axis. Okay, now I want to sketch these angles, all these possible angles. So starting from pi over 6, that would be 30 degrees. If, like me, you're more familiar with angles in degrees, then just think in terms of degrees. So that would be pi over 6, which is 30 degrees, 30 degree angle here, and I have to plus a whole number of pi over 3, and pi over 3 is 60 degrees. So if I add 60 degrees to 30 degrees, I get 90 degrees. Okay, so this is one. If I imagine that this is 2 units long, okay, so I have 1 roots here actually. I'll put a cross here, right? That's my roots. So if I add 60 degrees to this angle, I'll come here to 2. So that's actually another root. Okay. So the idea is that as n goes up in number, I keep adding 60 degrees. Okay, so the next one would be here. Another 60 degrees. And I'll be, from there would be 150 degrees. Okay. Carry on. Another 60 degrees. Another 60 degrees here would bring me right down to -2 actually. And another 60 degrees. Now from here, if I add another 60 degrees, I would come back to the same root as before. So I don't get something different anymore. So it's only this 1, 2, 3, 4, 5, 6 that are different. And in going from there to there, I would have gone from n equal to 0 to 5. Okay, that's what I get when I set n here to 5. Okay, now let's look at these angles. If I keep adding n from 0 to 5 to pi over 6, my angle will go from 30 to 90 to 150, and then this will be more than 180. Okay, this will be 210, which would exceed this, which will become more than pi. So that's not good. This is when let me write this out. This is when n is 0. Okay, this is n equal to 0 when I added this, and that's when n is 1. So n is 2, n is 3, n is 4, n is 5. So it's no good having n more than 2, okay, because when n gets to 3, that angle becomes more than 180 degrees, more than pi. So we don't want n more than 2. But how do we then get the other roots? Actually, there is another way. Instead of going up in n, I can decrease n. So if I can go to instead of going all the way to 5, I can say let n be -1. Then n would go in the opposite direction. So this can also be n equal to -1, and that n equal to -2, that n equal to -3. Right? Because if I put n as -1, then it would be 30 degrees minus 60 degrees. That means that from 30 degrees, if I'm minus 60 degrees, okay, if I'm minus 60 degrees, I would actually come down here to the same angle as this. So, and so on. Okay, so instead of doing this, I really need to use n equals to -3 to 2. -3, -2, all the way up to 2. So these are the values of n that I should use. Okay, and that's it. So I can leave the answer as that if I want, because these would satisfy the condition for theta that the question wants. Okay, so let's now move on to part 3. Oops. In part 3, we need to write z to the power of 6 plus 64 as 3 quadratic factors. 3 quadratic factors. So let's recall what we've done in the last question. We can make use of what we did in the last question. In the last question, we looked at z to the power of 6 equals to minus 64, and we got the solutions. And the solutions was given in this form: are z equals to 2 and then e to the power of z equals to r e to the power I theta, where r is 2 and theta are the angles given by, quickly sketch this out again. Let's see, 30 degrees, 90 degrees, and one here, here, and here. Okay, so it's given by these 6 points on the complex plane. Well, these are all separated by angles of 60 degrees. Now, and from part 1, if you remember, we have seen something about that if a polynomial has real coefficients, okay, then the complex conjugates is also a root, and that's the situation we have here. If I rearrange this, z about 6 plus 64 equal to 0. So this is the same as that. Okay, and the root is just as we know from part 1, each root has a complex conjugate. And from part 1, we also know, we have also found an expression for the factor, which has this form: z squared minus 2rz cosine theta plus r squared. So it means that this is exactly what we need to use for this question. Okay, all we need is to find this factor for r equals to 2 and for the possible values of theta. Now, and we don't have to use all 6 values, all right? We just have to use one theta, and we don't have to include the complex conjugate, because this already include, if you remember from part 1, this already included both the angle and its complex conjugate. So all we need is to take this one, and this one. All right, if I take this one and use it here, right, if I take theta to be this and use it here, then this would also include the complex conjugates. So all I need is to take 30 degrees, 90 degrees, and from here this angle would be 150 degrees. So that's what I need to do. So I need to know what is cosine theta. I need to write down this expression for these 3 possible values of the angles. Now, so theta can be 30 degrees, 90 degrees, and 60 degrees. Oh no, wait. From here, right, 150 degrees. So let me write down what this would look like. So that's z squared minus r is 2. So 2 times 2 is 4, z cosine 30. So cosine 30 degrees plus r is 2. So r squared is 4. So if theta is 0, one factor is this. So if we do it for 90 degrees, z squared minus 4z cosine 90 degrees plus 4. Likewise for this one, z squared minus 4z cosine 30 degrees, 150 degrees plus 4. Okay. Now cosine 90 is 0. So we know that that's 0. Cosine 30, let's see what's cosine 30 degrees. Now if you remember special angles, when this is 30 degrees for a right angled triangle, and if this side is 2, then this side is 1, and this side is root 3. So cosine 30 degrees is root 3 over 2. So this is actually root 3 over 2. And Cosine 150 degrees is on the other side, where this is also 30. So it would be negative, but also root 3 over 2. So this is root 3 over 2 with a minus sign. So with these values, right, we are not, according to the question, the answer should not be in trigonometric form, in sines and cosines. So that's why we need to write it out in surd form. Okay, so I think we finally have all we need to write out the three factors. So the first one would be this, z squared minus, so 4, and I have over 2 there, so they will cancel to give 2 root 3 z here plus 4. And next factor, z squared, that's 0 plus 4. Next one, z squared. This is very similar to this, but with a minus here and minus here to give a plus. So it's z squared plus 2 root 3z plus 4. So that's the answer. Okay. I'm just going to finish off by quickly explaining why a polynomial with real coefficients must have conjugate roots. So this is probably not required if for your A-level exams, if that's what you're studying for. But I'm just going to write it out for interest, in case you'd like to know. So if I have a polynomial with real coefficients, let's say it's of this form: a naught plus a naught z plus a1z plus a2z squared plus dot 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 plus a n z n is equal to 0. So let's say the z here is a root of this equation, and that the a, a1 and so on, they are all real. Okay. So the question is z conjugate? Is z conjugate a root? You can think of it this way. It's the same as asking, alright, or is this, if I write this out as, replace the z by z conjugate, that means that if z conjugate is a root, then a1z conjugate plus a2z conjugate squared plus dot 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 plus a and z conjugate to the power of n must satisfy the equation also, right? So it's the same as asking, is this true? Now, if you are familiar with the properties of complex conjugates, you would know that if you take the conjugate of this whole thing, and simplify it, you could actually end up with this, right, provided an is real. So you can actually get this by taking the complex conjugate. There are some detailed steps, some details involved, which I shan't go into, but very briefly, that's how you can prove it, right? Just by taking the complex conjugate of this and turning this into this.